Hi, my name is Luigi Rendon. I'm a member of the Japan Atomic Energy Agency at JPAC Center. And today I'm going to talk about multipacting study for the JAEA-ADS 5-cell elliptical superconducting RF cavity. Multipacting is an undesired resonant effect in which we have a large increase of the electron. This has a limitation on the performance of the cavity, particularly in the superconducting cavity. This is a main concern for the JAEA-ADS project, in which use superconducting cavities to accelerate a proton beam for energy of 2.5 to 1.5 gigaelectron volt. Therefore, to try to evaluate the effect of the multipacting in this project and find a countermeasure, we start to evaluate the multipacting for the elliptical cavity. Here in this table, I present one of the features of the cavity, like the frequency, the geometric beta, the accelerator range, and the energy range. We use two types of cavity, the so-called cavity 1 and cavity 2. We make the study using CST Microwave Studio. For that, we use the solver of Microwave Studio and the Particle Studio. The first one we use to develop the electromagnetic design, and the second one to make the tracking of the particles. As you can see, this is a full cavity model. However, we don't use that to simulate multipacting. We take advantage of the geometry of the cells, and we just simulate the so-called inner cell and end cell. However, we also want to push a little more forward and reduce. That's why we simulate just 1/4 of the cavity with elastical condition. And this help us to reduce the computational power. Then in this table, I compare the performance using the 1-cell model and the 1/4 model. Here I plot the emission current against different accelerator gradient in which will operate the elliptical cavity. And we can see that the two models have a good agreement. Another particular of this study is the consideration of the space charge. Usually people see kind of saturation in the emission current, and this is attributed for the electron, for the space charge effect. That's why we consider this effect. Here we can see how this effect reduces the maximum peak. However, we can still see that in this region, the multipacting occurs. For this type of cavity, for the elliptical one, we can see that the multipacting area is around to the equator. Therefore, to find a way to mitigate, we consider the idea to change just the geometry around the equator of the cavity to see if this can reduce the multipacting. However, we need to be careful because if we modify and we affect the geometry, we also can change the performance of the cavity. So we just change around the 10 millimeters around the equator to that. And we try to use different geometry, the so-called flat one, the round one in yellow, and so-called convex and concave. Here I present a kind of summary of the result. On the left, I present the emission current against the accelerator gradient, and we will start to operate it for the elliptical cavity number 1 and number 2, and for the so-called inner and end cell. We can see that for the elliptical cavity number 2, we have a larger emission current. And this is related with the fact that for the elliptical type number 2, the surface is bigger than the elliptical one. So that is the reason. Here, I make the test for different geometry for the inner elliptical cavity number 1. We can see that for the flat and round, the performance is quite similar to the original one, the flat one. However, for the concave, we see that they have a large increase, basically for low energy. That is related with the 2-point multipacting. And for the convex, we see an important reduction of the emission current. In order to have more, understand better how this geometry affects the multipacting, we start to evaluate the so-called geometrical parameter which is introducing here, which is the derivative of the normal electric field with respect to the transversal size divided by the magnetic field. This is introduced by Shemley in this reference. We can see that the p-value for the different geometry in this plot at different steps, let's say. And again, we see that for the original, the flat and round, the performance, the values are quite the same. For the concave increase, and for the green one, for the convex decrease. So we can see this relationship, and we can see that usually lower values of P can also reduce the effect of the multipacting. In conclusion, we see that we expect to have multipacting basically in the accelerator gradient range we will now operate the elliptical cavity. We saw that the complex geometry can reduce the surface emission around 48% with respect to the baseline design. We can see that this reduction is related with decreasing the geometrical value, the p-value, even though that the geometrical offers some advantage for reducing that. We also, this geometry represents a challenge for the cavity machine. Therefore, before to make a final decision, we need to start to make more study to see what is the benefits for using that against the challenge to make this kind of machine. Thank you for your attention.